midterm. So I would suggest that if you haven't started, probably start looking at the material, figuring out what you do and don't understand. Next Monday's lecture will be a review for the test. And that's what we'll focus on. So what I'll cover today will be kind of an outline of what will be in chapter 4. And you'll find that chapter 4, for some of you, is a little easier to understand. Most people find it easier to understand. So I guess it just depends. But that said, we'll have our quiz on Wednesday. And the quiz will cover something along the lines of moments, not moments. It's going to be, I was thinking about that, where I wanted to have it cover the end of chapter 3, the beginning of chapter 4. So I have to think about that. I'll send you guys out a quick announcement after the lecture when I decide what's going to be. The other thing is I have to be somewhere on Tuesday. So I won't be here in office hours on Tuesday. I normally have office hours on Tuesday from 1 to 3. So I will make those up on Wednesday. So if you have questions, normally I don't have office hours on Wednesday, so I'll reschedule it for that day. So, all right. So let's go ahead and start. All right. All right, so week 4. So week 4, you're going to finish chapter 4. I did want to mention the quiz. I apologize for not having them all graded yet. They're 75% graded. I'll be posting them. Not as many people got the complete correct answer as I was hoping, but most of you got pretty close, which is good because I know it might have been a time crunch on that one. I think I just want to point out a couple of things on the quiz that you guys did that I saw as kind of a common theme. First off is understanding this relationship, that the moment about a line is a scalar value, and that you have to have the unit vector of the line, EC. And I saw different permutations. I saw some people dot cross product, the unit vector with force. Some use the R vector as the dot product. So I realize that there's a lot of material and this isn't your only class, but if you need to write notes or whatever will help you, please note that this is the equation. It's always going to be the equation. You just figure out what the line is, EC. So going from E to C, figure out that unit vector, and then in the case of the two forces, it's around a common line, so you need to figure out a R vector going from E to A, and some of you are still going from the force to the line. Remember, you got to go from the line to the force. So it's A relative to E, meaning go from E to A, and I went from E to D. Now you could have gone from C to A or C to D, whatever, but most of you did E to D and E to A. Anyway, so the other thing was I gave you force 2, and this force here most of you got. The horizontal projection was 400, and then based on the horizontal projection, you knew that 3/5 of that horizontal projection was in the negative direction was your X value, and 4/5 of that horizontal projection was your Y. And so here are the respective forces. So once you had that and you had these, then it was just a matter of plugging it into the matrix and doing it. Now you can, because of the nature of this, you could have just added the 2 moments and then did the dot product. That's fine too. I chose to separate them out. And your final answer is about 21.8. So if you got 20, 22, 20, 20, that was fine. Some of you, I think, got 19.5. That was okay also, provided you did the correct process. And some of you made just some simple math errors, which aren't that big a deal in the big picture. So, I mean, of course, we want accuracy at the end, but a quiz isn't a realistic situation. So I try not to penalize you too much if you make a small math error because of the nature of the quiz. Okay, so I will post this solution. Please, if you're not understanding how I did it, it's real important that you come see me in office hours or figure it out because this stuff is going to come back on the final. Not the final, I'm sorry, on the midterm. All right. So next, chapter 3. So these are the things we've covered. These are the things you should be familiar with and understanding at this point. Forced couple systems, equivalent couples, and equivalent systems. So equivalent systems was the homework problem, like the last one where you had the 3 or 4 forces acting on a concrete block, and then you had to figure out the result. And those 2D ones are pretty easy for the most part. I did want to kind of go over an equivalent couple, or I'm sorry, a forced couple. It's a little more complicated. This was actually a problem that I did in the homework. I'm sorry, on a midterm a few quarters back. I think it was last spring I did this. And so in this example, and one thing I did this week that I hadn't done in the past is I sent you guys out last night the examples. So I sent you a Word document that has this problem and the other problems on it. If you didn't get it or if you didn't see it in your announcement that I sent, it's also on Canvas under the live lectures. So under the week 4 live lecture, I posted it there. So I thought this might be helpful for you guys to have the actual picture in front of you instead of having to try to scramble and write it down while I'm talking. Okay, so I don't want to spend a lot of time on this problem just because I want to move into chapter 4. But this one I thought was worth discussing. So just changed my camera. Bear with me. Okay, can you see my doc cam now? Yes? No?
Yeah.
Yeah.
Okay, thank you. Okay, so here's the image. And is it clear? You can see it. Let me see if I turn a light on if it'll help a little. There. Let me know. That's good if you guys just tell me if it's not clear or not. Okay, so this problem it's not super difficult, but there's a few things to keep track of. So in this case, you're taking this 9.8 pound force, and it's in the direction of this arm CD. And then you also have a 52 foot-pound moment attached to it. And then your dimensions in terms of from the origin are 4.2 going to this point here, and then 2.8 up. So we know what we can do is we can relate the force to where it is in space. We can then make this moment into an IJK, and then respectively, we're going to move this over to O. So we know that if we want to move anything over to O, it's going to be RD relative to O crossed with the force. And so, but in this case, we also have to add in, not only are we going to create a moment by moving the force here, but we also have to account for this moment. Now, remember that whenever you have a moment applied to something, it's a free moment. And what I mean by free is that it's acts anywhere on the object. So it's not bound to just being around this CD. It's just, you can just add it without its location. So what we'll do is we're going to break this up into components. So the first thing is we want to figure out is what is this 9.8 force. So it turns out that if we take FZ in the Z, it's going to be 9.8 cosine 30. And I'm going to write this quick because you guys know how to do these now. 8.49 pounds. And then our F horizontal projection is just going to be 9.8 sine 30. And that's going to give me a value of about 4.90 pound. Subsequently, I know that then Fx and Fy is going to be 4.9 times sine of 40 degrees. And
Professor,
yeah,
don't you need to unshare your screen or else we won't be able to see this work later?
I'm so, oh, you can't, I guess, yeah, because I guess I'm recording this. Yeah, there we go.
Well, you
Ah,
can switch the screens in the upper right corner of the camera usually, just so you guys know.
you can't, but can you do it if I'm recording though? If like, if I
No,
record?
not on YouTube.
I was
So,
able to. I could see your dot cam as my full screen.
Yeah,
oh,
I
you
just
could.
I enlarged the doc cam and then minimized the PowerPoint.
Okay, so it does work. Okay. Well, I guess if you guys already, since you have the image of the work I was doing in front of you, hopefully, since I sent it to you, that it's not as critical. So I'll leave it like this because I want to make sure you guys can see it. So um, everyone can see this now. Um, but thanks for the pointers because I don't, I should try some of this on my own to see what it looks like on the other end. So we got 4.9 sine 40 gives me 3.15 pound. And then lastly, we have 4.9 cosine 40. And that gives me negative 3.75 pounds. All right. So what we can do is we can make a unit vector out of this because we know that the 9.8 is obviously the magnitude of the force, and these are the respective components. So if I make what I call lambda dc a unit vector, because whether it's the direction of the force, the proportions are going to be the same, then what I end up with is lambda dc equals 3.15 over 9.8 I minus 3.75 over 9.8 J and plus 8.49 over 9.8 K. And the reason I want this is that this unit vector will then allow me to take this moment D and convert it to a vector, because right now I just know it's 52 foot-pounds. I know it's 52 foot-pounds, but I want an IJK so I can add it later. So I get MD, I know it's 52 times lambda DC. I know you guys can do that, so I'm just going to write it out. It ends up being 16.69 I minus 19.90 J and plus 45.1 K. So that part was probably the tricky part to figure out what you had to do with that 52 pounds. So now that you have this, then you just do your normal R D relative to O crossed with the force, which the force being what we found up here. So if we do our RD relative to O, and I'll just set that up, RD relative to O, we end up with negative 2.70 feet, 3.2, actually we don't put units in there, sorry about that, negative 2.70. And how I got that, unless you're just going from O to D, so you're just following it out the same way you would do with a projected force. So to get this 2.70, I'll just write out what I did. I had negative 4.2 sine 40. That was my I. And then 4.2 cosine 40. And that was J. And then 2.8. And that was my K. And then my force, of course, is just 3.15, negative 3.75, and 8.49. So do our cross products. And we get our final answer. What we end up with then is just a 16.69 minus 19.90 and plus 45.1. So this ends up being, this is my moment about D, sorry. Okay. So my moment about D, I take this, I add it to, oh wait, no, I'm sorry, I wrote the wrong one. I wrote that one. That was stupid of me. I rewrote this. This is this up here. Sorry about that. That's what happens when I go too fast. This ends up being, when you do the cross product of this ends up being 37.8 plus 31.7 and minus about almost 0. So this is then my moment about O. So effectively, the final answer, you just add this with this. That gives you your moment total. And so this plus this is your moment total. And then this force here. So that's your final answer. So it's basically this, we'll call it 1 and 2. So 1 plus 2 gives you moment total. And then this force that I wrote here. Because remember, whenever you do a force couple system, you want both. You want the force and the moment. That's critical. I know I went that kind of quick, but any questions on that?
I had a quick question.
Sorry, go ahead.
Go ahead.
I had a quick question. The lambda, you knew it was lambda DC because if you use like the right hand rule and with the way it was rotating, it's DC, not CD, right?
In that case, the you know I hadn't thought the in that case it's the direction of the, it is part, well I think part of it, you're right, is this is the 52 foot-pounds, but it's you're trying, if it's even simpler than that, because all you're trying to do is figure out the direction the force is going in. So the force is going from D to C. So that's why we're making our unit vector go from D to C.
No, but when you're trying to find which direction the moment vector is, that's it.
Oh, well, the moment, the 52 foot-pounds, that's just a scalar value. So all I did was multiply that by lambda DC, which is going this direction, right?
And you knew it was DC because it was I'm just saying, how do you know it's not CD? Is it considered the right hand rule? You curl it around and it goes in that direction?
It's going, oh, I see what you're saying, is why isn't it coming back at you?
Well, I think I know why. I just want to clarify.
Yeah, I mean, that's one, I mean, I guess, yeah, you could look at it that way because of the right hand rule. When your fingers curl, because it's going counterclockwise, it's pointing up and away.
Yeah. Okay. Thank you.
Sure. Any other questions on this one?
Yeah, it was when you were doing the cross product, you went from the new point to the old point, right?
Yes, that's correct. So my R vector goes, it's D relative to O. So it's O to D.
Oh,
So
okay.
you always want to go from here up to that to find your R vector.
But when it's a moment about a line, you go from anywhere on the line to the force, right?
Which
So
is,
it's the
well,
same
it's
concept.
it's the same idea, because here we're taking a moment about a point, and this is where our force is. So we're going from the point to the force. So if we're
Oh,
taking,
okay.
yeah, so it's always from the point of the moment to the force, wherever the
Okay,
force is.
got it. Thank you.
All right. Okay. So let's go on and talk about chapter 4. And oops. Oh yeah, okay, sorry. So okay, so chapter 4 deals with equilibrium in 2D and in 3D. And it's pretty much applying the stuff that we did in chapter 2, which we first learned, where you take the some of the forces in the X, some of the forces in the Y, and you can take moments about points. We didn't do a lot of moments about points actually in obviously in chapter 2, because we're just learning how to do vectors. So now that we understand moments about points from chapter 3, then we combine these to solve. Now, typically in 2D, you only have 3 equations that you can use: some of the force in the X, some of the force in the Y, and some of the moments about a point. And so generally you'll have 3 unknowns that you need to find, and that's it. When we go to 3D, it becomes a little more complicated, but it's still, I could call it kind of recipe, because you're still doing, each problem is approached almost the same way. The first and foremost thing with this stuff is drawing good free body diagrams, and that's something that you need to get down as a good habit, not being sloppy, using a straight edge to draw them, because these are going to come back to you in dynamics and CE204, other classes. And so the better your habits are here, the better off you'll be in other courses. So what I want to start off with is a simple equilibrium 2D problem. And here we have this. So what we have is a bar, and it's between 4 sets of wheels. And so the first thing I want you guys to do is take a minute and draw what you think would be the free body diagram for this. So you want to draw what reactions are occurring on that object. So take a second to do that, or a minute to do that, and then we'll talk about the problem. So you may not be done yet, but here is the equilibrium that I put up, or the free body diagram. And so in this case, you have, as you suspected, you have the 300 newtons, you have the 2 forces on C. Now, the thing that's kind of interesting about this is you have wheels on both sides of it, but in the context of the problem, only one side is going to make contact. Now, if you think of this thing mechanically, and that can be sometimes hard to visualize, but the more you look at it that way, the easier these problems will be. If you're pulling down on 300, if you imagine like your hand, you hold your hand at about 30-degree angle and you pull down at 300, then most likely what's going to happen is the bar is going to pull down into C, but it's going to be pushed up into B. So because of the way it's going to tilt, especially with that 4,000 Newton meter moment, because it's going to try to rotate it in the counterclockwise position. And so it's going to push B up, and it's going to push up into B, the top B roller, and push down bottom C roller. But for the purposes of free body diagram, you can draw it how it is here. And then when you actually do the calculations, it'll determine whether your directions are correct or not.
I had a quick question.
Yes.
So even though it might seem like there'd be 2 contact points on both C and B, I guess because you're pushing down, it's probably more likely like it's probably just going to touch only one of the wheels. So only one C and one B arrow is needed.
Yes, that's correct.
Okay.
And if on a test or something you drew both, that wouldn't be the end of the world. I mean, you would just, what you would find at the end of the problem, and this is what I did on my, so let me go ahead and pull up my screen. So here's my screen of my free body diagram. So what I've done is I've gone ahead and I've drawn CY, BY, and I've drawn these up here just kind of markers just to show that there is a potential reaction there. I also tilted the axis. So I'm calling this CY prime and BY prime. And you'll see that in a second. We know that's 30 degrees, that AX reaction there. And we know that this 300 newtons is straight down there. So how do we solve this problem? So, well, we have how many unknowns? We have 3. We want this, we want this, we want this, and we have 3 equations. So we know that we can sum the forces in the X to 0. And let me just move this over a little. And we know we can sum the forces in the Y to 0. And we can sum the forces in the, I'm sorry, not Z, I was about to say that. We can sum the moments. And where it depends, but we can't, we only have limited options with that as far as points that'll help us. So first equation, let's go ahead, we'll sum the forces in the X to 0. And in this case, I'm going to go ahead and I'm keeping my XY axis. So what I'm going to say in this case is I'm going to say CY prime sine 30, because that's going to be, right, we know that it goes like that. So this is this part of the force I'm getting right here. So CY prime sine 30, and then plus BY prime sine 30 minus AX equals 0. And so if I simplify that, I end up with CY prime plus BY prime equals 2 times AX. So there's one equation. So then I go and I could do the same thing. I'm going to sum the forces in the Y direction to 0. In that case, I have negative 300. I have plus CY prime cosine 30 plus BY prime cosine 30, and that all equals 0. And so if I simplify that, it ends up being CY prime plus BY prime equals 200 times the square root of 3, which is about 346.4. All right. So now that's equation 2. So 1, 2, and then, so then we have sum of the moments about A to 0. And so that gets rid of that unknown. And so if we do that, and the reason we're summing the moments about A is because we want to get rid of that unknown, and we want to again get, we have A in this equation, so we don't want it in another equation. We want to basically get 2 equations with just C and B in them. That way we can solve. If we have 2 equations and 2 unknowns, we can solve that. Then we can come back up here and solve for A. So that's kind of the idea behind it. So we end up with, if we sum the moments about A, we end up with 6 times, and remember these are in feet here, so 6 times CY, so that's 6 feet from A, right? And it's going, in this case, it's going negative, so it's negative 6 CY prime minus, let me draw it the way I normally do. I normally write it with the foot afterwards. So minus CY times 6. That's just my own neurosis. So, and then minus BY times 2. And then plus the moment of 4,000 Newton meters, because it's a positive moment. and then plus 300 cosine 30, and then that's times 8. Now equals 0. So all I did was account for all the forces, everything acting at A, right? You have By pushing a distance of 2, Cy a distance of 6, the 3000 going counterclockwise at a distance of 8, but only part of it's going just to cosine 30. And then of course you have, which sorry, I didn't write that in, the 4000 Newton. So definitely write in every force. So that's my mistake. I apologize for leaving out that moment. Got ahead of myself. But you want to, so the important thing about the free body diagram is to, you don't worry so much about putting in dimensions. If it's easy, like in this case, go ahead and write 242. And then you can always write, somewhere in your problem, you write dimensions. I usually try to write dimensions and then write, feet, or I'll write units, feet, pounds, something to indicate that, that's fine. I don't usually use ticks like this. That's not really true units. I mean, we all know what it means. It means feet, but it's probably a bad habit to do, so I wouldn't do that. You may see me accidentally do it occasionally because it's hard to teach an old dog new tricks, but nonetheless, you're clear, new minds shouldn't. But getting back to this, don't worry a great deal about getting all the distances in. The important thing on any free body diagram is to write the reactions and the forces and or moments that are there. Okay, getting back to this. So we have this. So if I simplify that, I end up with making it ends up being 6 cy prime plus 2 by prime equals 6078. All right, so we have that. So what I'm going to do then is I'm going to take this equation up here and I'm going to multiply that by a -2. So if I multiply this by a -2, I end up with -2 cy prime minus 2 by prime, and that equals a -400 root 3. So we'll go ahead and add those together, and we get 4 cy prime equals 5,385. So solve for that, I get cy equals 1346 newtons. Now I have cy, so let's go back and plug it into this. And you might notice that this is, so when I plug this in, I'm going to have 1346 plus by prime equals 346. So this by then is essentially -1000. So that means that up here, since it's a negative, it means I was wrong pointing it this way, that it actually does point down. That doesn't mean you have to change your free body diagram after the fact. You just report this number as a negative. And then in reference to this, that will imply or state that this actually makes contact here, which is what we would expect, right? If I twist my pencil, it's going to want to do this, right? If it's spinning around the center point, it's going to want to go up and down. So it makes sense that the reaction is going to be here and here. Anyway, so we can take these numbers and plug them back in up here and solve for AX, and we get AX equal to 173.2. So, and all of this, of course, being in, so we have newtons. Oh, wait, these are meters, aren't they? Did I say feet? Did I say these are, is this newton meters or feet? Yes.
I think it's feet.
It is feet. Okay, thank you. So I don't know what I was thinking here. That's what I thought. And I wrote newton meters by habit because that's usually what we have. So yeah, so we have, I'll never mix units in a problem. So that was So you always have pounds. So we got pounds, 1,000 pounds, 172.2 pounds. Any questions on this? So I think the math itself is straightforward. I think it's understanding, what are you actually doing up here is the important part. How do you approach this? How do you actually solve for this? And make sure that you account for it.
I'm
So
confused. So what?
Sure.
Why you put CY and BY prime? Like, what is it about them that makes it prime?
Oh, the only reason I put the prime there was to show that they match this, that they're on this axis. That's all. See, I made the Y prime, X prime. They're still CY and BY. They're still the final answer. So you don't have to put the prime there. I did it just to show that I'm accounting for them on this axis. That's all.
Okay, if they're on that axis, then how come we still use like the sine and cosine of the angles for their
That's-
value?
Yeah, that's true. So it's a good question. Well, you're right. I mean, I guess we're saying that they're. I guess in my context, I'm saying that they're in this. That's the direction of that. But when I do the sum of the forces in the X, sum of the forces in the Y, I'm using these. So I think that that might have been maybe what that might have made things confusing. So you could have gotten rid of that prime and it really wouldn't have mattered. So sometimes it helps to alternate. And then because this problem could have been solved two ways, you could have solved it with having it be 30 degrees. And then you would have just treated this when you did the sum of the forces in the Y, this would have just been CY and BY. And then the 300 would have been minus 300 cosine 30, right? So I guess that's a good point. If you want to just think of it as CY and BY, that's fine.
Okay, I just wanted to make sure, see if we could solve it with the new axis and do it that way. But it sounds like we can. So thanks.
Well, I think you could. It's just going to be a little more cumbersome because by keeping it the way I did is that keeps AX horizontal. But I haven't tried it that other way, and so I guess I should have left this primes out. So I apologize if that made any confusion. But most of the time, what you'll find with these problems, with the 2D equilibrium, is that you will start off with a free body and you'll have your two equations, sum of the force in the X, sum of the forces in the Y, and then you'll take a moment about the point with the most unknowns. So in another universe, this problem, maybe it had a Y component too. In which case, in order to eliminate that, you would always take your moment about that point with the most unknowns, and that would allow you to solve it. So if you completely ignore this and just forget about it, then everything I did would still work fine, right?
Yeah, that makes sense.
Yeah, so that's probably a better way to do it. Okay, any other questions on this one?
Yeah, about having that AY, because the beam is resting against the wall, there's going to be only one component. Unlike if it was like a joint, let's say.
That's correct. That's why you only have the single reaction and you don't have friction. If you had friction, then you could account for, then there would be a upward reaction, but you're right. We won't, in chapter 4, there will be no friction. So the only way that you could have had a reaction would be like a pinned joint. And so reaction types, if it's not on there on Canvas already, I'll post it, but I have a page of reactions. It's better than the one in the book. It shows all the different types of reactions. I go over them somewhat in the recorded lectures, but most of the reactions that we deal with are in 3D or ball and socket, which means that they support forces but not moments. So there's a whole there's a hierarchy of different reactions. And so when you think of a reaction, if you have, for example, if you have a pole, in the ground, right? Let's say you have a pole in the ground and this is your pole, and this is in 3D, then if this pole is cemented in the ground, then effectively it can support a moment around each axis, and it can support a force reaction around each axis. So it basically has these 6 unknowns at this point. If I take that same thing, and let's say instead of having it concreted into the ground, I have it set so it's what's called a ball and socket. And it looks kind of like that. It looks like I guess the best way to draw it is like this. It's like a little pyramid with a ball on the top, and this comes down to a point. If you have something like that, then it can only support force in each direction, X, Y, Z, but it cannot support a moment. So in a 2D, you have something similar. If you have like if you have something pinned on the wall, then it can support, force AY and AX, but it can't support a moment. So it's free to rotate about that pin. Whereas if you took that same beam and you had it into the wall, then this could support a moment. So it would be, the way you draw it is you'd say moment about A, and you'd have AY and AX. So in order to solve these problems, you have to identify how many forces you have, and what the reaction can do. So this is the most complicated, right? Because you got 6 unknowns, and all the way down to where you just have something resting on the ground on a frictionless surface, and where the reaction is just a single. So this is the part that you kind of got to work through and understand. I can't cover it, and we only have 5 minutes left. So, but the problem I was going to do next, which I'm not going to get through, but I wanted to kind of let me just kind of detail it for you, and you'll have an example of this in the homework to do. And the homework, this next coming assignment isn't due next Monday. I think I'm going to have it due. I'm not sure what the date is, but I think I'm going to have you guys turned in on the day of the exam, mainly so that you can have it up to the time of the exam to turn in. Not to add more stress to you, but that just gives you a couple extra days so that you can have it. Now it's kind of weird because I say have it, but you submit the homework via a file, so it's not like you give it to me and don't have a copy. But this, I think, will give you a little extra time with it. But so let's look at, in the couple minutes we have left, let's look at the last problem. And so that's this one here. So this one, what you have is, and let's talk about this, because we don't have time to solve it, but I can give you kind of an idea what you're going to do, what you would do to solve it. So you have your beam OC, and this, you see how it says ball and socket. So this point here at O, what you see is just a ball and socket. So that means you just have an OX, OY, and OZ, but no moment. You have the tension AD and the tension CD. So first step, can draw the vector for AD and AC. I'm sorry, AD and CD. So you're going to basically create your tension vectors for that, knowing the directions. And then your free body diagram, of course, is going to consist of, the free body diagram is of the actual pole. So your free body diagram looks like this. So you have the force, you have the load, and then you have 3 forces here. And then there's your original drawing here. So just like we did in the other problem, you're going to end up summing the moments about this point here. And when you do that, the only difference is, in chapter 3, when we sum the moments, we did R cross F. So you're going to have an R vector going from here up to this, and an R vector going from here up to this, and an R vector going from here to 0 up to P. And when we get there, we're going to then set up a series of R cross tensions, which would then, they're going to look something like this. So you'd have your R vector, because you're going just from O to A, it's just simply 3 meters in the 3 meters in the X direction, or I'm sorry, the Y direction, and then 5 and then 6 respectively. And then you have your respective tension vectors, right, with their unit coefficients in front. And you set all these up, and you basically set them equal to 0. So you have this plus this plus this, all equals 0. So you go ahead, do all your cross products, separate them in IJKs, solve, and you get CE and AD. And then the last step is to then sum the forces in the X, Y, and the Z, and solve for X, O, Y, O, Z. So it sounds like a lot, and it is the first couple times you do it, it's a little tedious, but we will talk about that next week. You do have a couple example problems in the lecture. I would encourage you to make sure you understand that. High probability that a question like this 3D will be on the midterm. Okay, so if you study nothing else, I would make sure you understand this. I apologize, ran out of time. I did want to go through this one in more detail, but we will have opportunity to discuss it on Monday. Any questions? Okay, we're out of time. I will email out something about what the quiz will cover, just so everyone's got it. And the quiz will be the normal time from 8 to 10-ish or so on Wednesday. Thanks, you guys. I'll see you in office hours.
Professor, I had a quick question.
Yeah, what?
It was more just about like personal matters in this class. It was
Okay.
just
All right. Well, ask me in office hours. Okay.
okay. Perfect. Thank you.
Okay,
Can-
guy. What?
Oh,
Go
can
ahead.
you just go back to that slide with the quiz 2 answers?
Yeah, I'm gonna post the quiz. I'll post this answers to it.
Okay.
Yeah, I'm gonna put that up there. I'll put that up there after I'm done with class. I have another class after this from 9 to 10. Okay.
All right.
All
Thank
right, you guys. Thanks. We'll see you next time.
Thank you.
I had one question.
Yes.
So about the, I guess, the moment equation, the R cross F dot product with lambda.
Right.
The answer from that is a scalar value, right?
Yes.
Okay, shoot. Okay.
Okay.
Thank you so much.
All right. Thank you, guys.